Hey, my name is Simon Vesta, and this is Lab 5, Magnetic Molasses. So the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare computational predictions with observed data. So for every preview of the results, the average time the magnet took to fall through the tube was 1.476 seconds, and the time for the computational model for the magnet falling through the tube was 1.317 seconds. So for assumptions, air resistance was considered negligible, and the only forces on the system are magnetic and gravitational. And lastly, the barred magnet acts as a magnetic dipole. So the fundamental principles include Biot-Savart law, Faraday's law, Newton's law of motion, Newton's second and third, where third is for every action there's equal and opposite reaction, magnetic forces, magnetic flux, and Ohm's law. So the experiment was the aluminum foil and bar magnet, and surroundings everything else. For initial conditions, the magnet was at rest above the tube, and for procedure, first we assigned the end pole to the bar magnet using the magnetometer app. Then we measure the mass of the magnet, then measure the width, inner radius, and length of the tube. Then drop the magnet through the aluminum foil, recording the time it takes to reach the bottom, and finally repeating it for a total of 5 drops. So the average drop time for the magnet was 1.476 seconds. The tube dimensions include length of 0.3 meters, width of 0.007 meters, and inner radius of 0.025 meters. And lastly, the mass of the magnet was 0.023 kilograms. So here's the computational model code. First, constants were put into the code, including length, width, inner radius. The total radius was calculated, and then the mass and the magnetic dipole moment was imported from lab 3. Then the magnetic field was calculated, and the change in flux was also calculated using the formulas stated previously. Next, there's a time loop, which calculates the magnetic force on the magnet and also the gravitational force. And then the velocity and position of the magnet are updated, as you can see here. So this is the model that the computational model created, and pretty much in the beginning of it, gravity is greater than the force of the magnetic force, and then in the middle, the gravitational force is equal to the magnetic force. And at the end, gravity is again greater than the magnetic force. And the time it took to fall was 1.317 seconds, which is slightly faster than the experiment. Interpreting simulation. The intensity of the color in the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and what's is counterclockwise? How can you know? So using Lenz's law, it's found that red is equal to counterclockwise, which is above, and blue is clockwise, which is below. What happens to the dynamics of the system when you flip the magnet around? Well, nothing physical would change, but the B field and B induced fields would flip. How does the total time in tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? Well, the computational model is already somewhat accurate because it's only like 0.1 second off. But if you account for air resistance and not having any human time errors, the drops, it can improve accuracy. Lastly, what is the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, the gravitational force is greater than the magnetic force at the beginning and end, and the gravitational force is equal to the magnetic force in the middle. So for possible errors, for human, I could have inaccurately timed the drops for each trial, and possible contact with the tube and magnet could have been made, which causes friction. For computational errors, I could have incorrectly created the computational model on GlowScript. Discussion. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, the induced current would increase, the magnetic force would increase, and the magnet would fall slower. What if holes or slots were cut into the tube? How does this affect the ring currents in your model? Well, the induced current would decrease since holes were disrupted, and the magnetic force would decrease, causing the magnet to fall faster. So in conclusion, we successfully collected observational data of a magnet falling through a conductive tube of aluminum foil. Modeled the magnet-tube interaction computationally, compared computational predictions with observed data, which is relatively accurate as shown by the similar times between the computational model and experiment, and magnetic fields overall have visible effect on daily life that can be seen if you look hard enough. Thank you.